So, today we will continue with the wave spectra and try to finish it. Now, before we go into the deeper discussion, let us first have a look at what are the statistical parameters of the ocean waves. So, here you write parameter, then symbol and description, because often we will come across notations for these parameters, especially you will find in the spectra definitions. So, you may not be knowing. So, parameter number 1 you write short term record, say short term record. Record means wave record for a certain duration of time. Now, here we denote this by the time period T s, and this is called the duration of the storm. So, some of the terms are typical to the oceanographers, duration of storm, and in mathematical terms you can always say that this is a significant time period, significant wave period. So, this is also important. So, all these things you will learn in detail in your oceanography class, but since in our case we have to come across in our spectra. So, next to this is your significant wave height. So, this is denoted by HS. So, commonly you will find these coming in your oceanography class, this HS and TS. So, this is the average height. Now, this HS is very important from this point. You will find this is called the average height of the highest one third waves, or rather you write 1/3 waves. Now, this is done in a short term record. Short term record. So, if I give you a wave record of the wave heights, how do you calculate HS? So, in a descending order, you take the wave heights, you make a chart. In the descending order, you plot all the wave heights and take 1/3 of the highest. You take 1/3 of the waves from the highest 10 and mean of that, that is the average, means the mean will give you the HS. So, HS and TS is also called the significant wave period corresponding to this value of HS. You will get short term record. Actually, here it is normally you take wave records for say 15 minutes. Long term record will go for say few days or few months. So, here this is the crucial point, and the other one you will come across is called the root mean square, RMS. So, those of you who have done a little bit of statistics will come across this. So, this is called RMS wave height. So, in short they write H or RMS. So, this is the root mean square, root of the mean square wave heights, value of individual wave heights. Individual wave heights. So, RMS, we will see where this comes, and the other one is called the peak frequency. Now, all of you must have had a look at the spectra. You have a look, you turn your pages and see the spectra, and there you will find the peak frequency. Now, this is denoted by omega naught. and this is called frequency at which the spectrum peaks. That is the largest value of the spectrum, that is called the peak frequency. You find in your wave record you have plotted the EF as your spectrum is like this. So, this is your omega naught. So, this is your EF versus what F. So, this is your peak frequency. So, this is another parameter which is important. Now, I have already given you spectra for John Swap and Pearson-Moskowitz. So, today I will give you two more spectra. Now, let us finish this definition. Then significant wave frequency. So, this is number 5 is significant. Actually, all this in details we will study in another course, that is called ocean technology or offshore technology you are having in 4th year. So, it is very difficult to cover all the aspects in one course. So, this is called significant wave frequency. Now, this symbol is given as omega s. Now, so this is the average frequency corresponding to the significant waves. Corresponding to significant waves. So, all these are related, your omega s, Hs and Ts, wherever you come across this S, this stands for significant. So, that simply you remember that, no point going into all this. The other one is the mean frequency. So, that is your omega bar. So, this is simply the mean. Mean frequency of the individual waves. Now, all this pertains to short term record, not long term. Mean frequency of the individual, I am not writing short term in every case, but it is understood. Mean frequency of the individual waves. Last term is not that much used, but still this is called the wave standard deviation. So, those of you who are not familiar with statistics, they just you look up any statistics book. Now, in my previous class, I have already talked about variance. Now, what is the physical meaning of this variance? Why it is called variance? That A square or that EF term. The variance means varying with what? Variance means variance is the statistics. What is the definition of a variance? Variance means a particular the number which is deviated from the mean, and you square of that. Now, in the elevation that you have done, where I have talked about the mean elevation is taken as 0. That is where you are getting the square term. So, that is one of the interpretation why we say that is the delta var is the variance. Now, here you have wave standard deviation. So, standard deviation is root over variance. So, this is called the standard deviation. Sorry. So, you just look up any statistic books, you will clear this, what is called the variance and standard deviation of wave time history. Wave time history. So, these are some of the definitions. Now, let us go to the spectra. Now, spectra, I have given you the two formulas of, one I have given you was called the Pearson-Moskowitz. This is, I think this is the spelling, Moskowitz. And the other one which is important is the John-Swap. This is your joint North Sea wave project. Now, these two spectra are important. So, this is your wave spectrum. Now, John-Swap is actually a extension of your Pearson-Moskowitz. You see in the Pearson-Moskowitz, I have added one more term, then you will get John-Swap. But where you are going to apply Pearson-Moskowitz and where you are going to apply John-Swap. This is very important if you want to do structural analysis. Now, Pearson-Moskowitz is normally applied in deep water. So, this is actually a deep water spectra. Now, in deep water actually you will find waves get dispersed. So, that means if you come across your hydrodynamics or your oceanography, that is the various waves get dispersed in deep water, whereas John-Swap you apply is more applied in coastal waters. Now, in coastal waters what happens? You find that John-Swap has a sharper peak. John-Swap will come like this sharp peak, and Pearson-Moskowitz will have a more or less a Rayleigh distribution like this. The peak is more having a curve like this. So, here actually this is more applied in coastal waters, dispersion relationship, waves are not dispersed. No, waves are not dispersed. Why? Waves are not dispersed because of waves in shallow waters, they do not get dispersed to other frequencies because of bottom friction. Bottom friction. So, that means in this case this is a unidirectional spectra. You apply unidirectional spectra. So, I have given you two spectra, one is the theta term, that is your directional spectra, and the other is the unidirectional spectra. So, unidirectional spectra more or less you apply John-Swap model for coastal waters. So, actually you have to be careful where you apply the spectra. Now, there are other spectra also. This is called Brett-Snyder, but this is a little bit outdated now, but it was widely used at one time. This is called Brett-Snyder. So here you will find this Bresneider is given as S omega. Omega is your circular frequency, and this is S omega is that E omega. So this is given in some other expression. This is 1.68, 0.1687. Hs is your significant wave height. Similarly, your this is omega s is your significant wave frequency divided by the wave frequency, and this is multiplied by exponential is e to the power minus 0.675, and here is a non-dimensional term omega over omega s. This is raised to the power minus 4. So this is called Bresneider. Now the other spectra that is of interest is the ISSC spectra. ISSC stands for International Ship Structures Committee. So if you want to doing structural analysis, you can take help of this spectra. ISSC gives this formula. So sometimes in this you write International Ship Structures Committee. Now sometimes you will find this expression in your ABS book, American Bureau of Shipping. Those of you who are consulting ABS or mobile offshore drilling units, they will come across this ISSC spectra. So this is given by International Ship Structures Committee. So S omega is given as 0.1107, and this is HS. So we are more interested in our ocean engineering class the behavior of the offshore structures with response to the waves. So here actually the mean value is taken, and the exponential term, that is e raised to the power, this you just change the factor, this is 0.4427, and this is again omega by omega bar to the power minus 4. Same expression is a bit modified only. So these are the 4 spectra with which normally the oceanographers come across, but normally other countries, especially Japan, I don't have the you make your own spectra, that is for design. Now offshore structures are, you will find they are very much, see, offshore structures are site specific. Offshore structures are essentially site specific, especially your fixed platform or your floating platform, they are fixed at a particular location. So they are site specific in nature. Now if you want to do say build an offshore structure in say Gulf of Mexico, now this GOM, in short it is called Gulf of Mexico, will have a different spectra than in North Sea. So different from North Sea spectra. Then what you are going to do? So you have been given a specific task of designing a say fixed structure in Gulf of Mexico. Now Gulf of Mexico is having different from North Sea spectra. Now you say that your professor has given you John Swap, Bresneider, ISSC and all these formulas. Now, here if you do not have any spectra, you go for deep water. Either you apply this Pearson-Moskowitz or John Swab. Now many countries, they have started developing their own spectra, especially Japan. Now, Japan actually does not go for either Pearson-Moskowitz or John Swab. Japan uses their own formula, that is called the Goda spectra. Now, this I do not have in my book because it is not written by Japanese. So, they use this Goda spectra. So, you will find they have done lot of research, they have taken lot of data along the coast of Japan, and they have made their own spectra, that is called the Goda spectra. So, this actually requires a lot of data analysis, which the other countries which are interested, they can do, and where if you do not get this, then you can blindly apply Pearson-Moskowitz or John Swab. Now, John Swab actually has been developed from a project that is in the North Sea. So, it may not be applicable to other locations in the globe, is not it? So, for to be more specific is better to develop your own spectra, develop own country spectra. But in our country, I do not know whether your National Institute of Oceanography had done that or not, but nowadays I think they are doing it. So, develop your own country spectra to be more specific. Now, this is used in the offshore structures. Now, so this is the discussion of spectra. Then next, let us have some idea, since we are dealing with the sea, what is the sea state? So, definition of sea states. This is actually a layman's knowledge, but for more scientific definition, if you want, then the oceanographers, they always refer to the spectra. But since the common man, he is unable to interpret what is the meaning of a spectra, he normally goes by a sea state definition. So, normally you will find sea state, there are various descriptions. So, this is description of the sea. Then it is described with respect to a certain wind speed. Wind speed range. Why? Because most of the waves are created by wind. So, that is called a wind generated wave. So, this is your significant wave height. Significant wave height, and this is wave period range. Now, in this table we have given a wave period range. So, normally this wind speed is given in knots, and wave height, in here you can convert the feet into meters, and this is given in seconds. So, sea state 1, this is the least of the waves. So, here you will get small wavelets. Wind speed is now 5 to 10 knots. Wave height is pretty small, only 0.3 to 1.4. But these are all significant wave height. Now the corresponding period that you will give is 0.5 to 5 seconds. Wave period is your T. So these are your HS values. HS you write TS. Now next is C state 2. This is large wavelets. So this is 10 to 14 knots. This is 1.4 to 3. Significant wave period is 1 to 7.5. Number 3, you write small waves. So here it is still larger, wind speed 14 to 18, and this is we are getting 3 to 6, and here is 1.4 to 8.8. Now 4 you get moderate, small to moderate. Small to moderate is 18 to 19, 6 to 7, and this is 2.5 to 10.6. Last is moderate waves. So 19 to 24. Now actually what is this wind speed, you may not be able to remember, but these HS and TS values you simply have, you take note of this, right? So 19 to 24 is given 7 to 13. 7 to 13 is 2.8, sorry, this is 2.8 to 13.5. And sometimes in your interview they will ask you what is the significant wave period and wave height. So 6 large waves. So if anybody asks you, you give the value of this moderate waves. Difficult to, so 7 to 13 feet will be how many meters? Say around 4 meters, 3 to 4 meters. You just tell that it is about 3 to 4 meters, and wave period you tell say 10 seconds. So just off the shelf answer. So large waves you get 24 to 30. So here we are getting 13 to 22, and then it is 3.8 to 15.5. So then is now actually from waves we are going to storm conditions. Now this is actually more important for offshore structure design. So this is, we are coming to moderate gale. So when you design an offshore structure, you have to design for the storm conditions. So moderate gale is, now the sea is actually becoming more and more rough. So you are getting 30 to 40. So and this is 22 to 45. So this is 4.7 to 21. Then strong gale. Now whenever you design an offshore structure, you look for these three conditions. So 40 to 55 you are coming. So this is 45 to 70. And this is 6.5 to 25. So wave period has increased. The last one is hurricane. So this is sea state. Normally these are given in a scale. It is called Beaufort scale. You will come across this Beaufort scale. So hurricane is 55 to 70, and we are getting 70 to 115 feet. 10 to 30 seconds is significant wave period. So 115 feet is how many meters? 115 is actually, this is 30 meters. So hurricane conditions you will get at 30 meters. So these are frequent in Gulf of Mexico. So Gulf of Mexico offshore structure to be designed for hurricane condition before 10, and but this statistics has been taken over, I don't know, this time period. There were this significant wave height for how many waves they have taken, but normally if data is not able, you try data for 25 years or 100 years data, collect data for 100 years. So that is the maximum that we have got. Now after this, let us come to another important factor before we wind up this spectra discussion. It is called a response spectra. So we are more interested in studying the response of the structure to waves, isn't it? Ocean engineer, he is more interested with response of structures to waves. Now, what is this structure response? Naval architects, they are more interested in response of structures to waves. So what is this response? Now response can be number one, pressure. Pressure is a response. Pressure is force per unit area, or sometimes you write this as force. Now what is the other response? Others are basically motion response. Now what is the motion response? We are interested mainly in heave. Heave is, I told you in your offshore engineering class, is a very important response of offshore structures, because if you get too much of heave, you have to stop drilling or taking oil from the well, because that will snap your marine riser. Now next important motion is pitch. So all these motions you study in your seakeeping class. Now basically in your vibration you have to formulate your equation of motion for all these three states, 1, 2, 3, 4. The other one you get is roll. So in your seakeeping class you will be told how to formulate this equation of motion in heave, pitch and roll. So I'll give you a glimpse of what is there, it's stored for you. you write down, or you have to find the displacement for this. This we have already discussed in your vibration class, and this will be how much? This will be f. Now in linear waves, write this as cos omega t. So this is your excitation force. This is your excitation, and this is from this this is basically your response. So there is you have to strike in all these three conditions. You have to formulate this equation. So this is another study by itself, which of course you will come across. This is called sea keeping studies. Sea keeping is nothing but study of motion or motion response. Now, I will just give you some inkling of what is this, since we are discussing spectra. Now, there are two things that is important. One is you come across what I have told you is excitation and response. These are two things which from the equation of motion, excitation and what is the response. Now, how we are going to study this? Now, this is best studied by what is called a transfer function. You have to formulate a transfer function where you are going to transfer the excitation to the response. So, in structural engineering, we are more bothered about this. So, this is of interest to your structural engineer. Now, this transfer function you must have come across in your study on this is feedback and control. In electrical engineering, you must have studied, I do not know, they should have taught you about this feedback and control. So, there also you come across this transfer function. Now, in simplest term, you write excitation. Suppose our excitation is nothing but wave excitation. Now, excitation you write in small x. Now, this gives an output. So, all these terms you will find in the signal processing. Signal processing I do not know, because this this feedback and control and all these things will come under this. Say output is your response x t. So, what we are getting is that there is a transformation from a excitation to the output. Now, this is small x and this is capital X. I am writing you. So, this is, let us say this is one wave. Okay. So, number one excitation. Now, number two excitation you write from another wave, you are getting this. Now, I told you that the C is represented by a summation of harmonic waves. So, here you get another y term. Say another wave is coming with y t, and this is giving another output, and this output you write as capital Y t. So, here y t is giving, this is giving x t and this is giving capital Y t. So, now when you add these two, you have A x t plus B y t. So, this is your input, your input is your excitation. Now, you just add linearly, there is a linear addition between this x t and y t. The only thing that you have to do is multiply by the amplitude of this wave, where x t is having an amplitude A and y t is having an amplitude B. Now, what is to be noted? You just see the response. So, here this is your excitation and this is your response. So, this is excitation and this is your response. Now, one thing you note is that these amplitudes will remain the same. So, x t will give you capital X t forward, plus you have the same amplitude of your response, but your formula in the harmonics will be different. Now, here say x t, you write this as your sine function. X t, you write this as, you put a small cap on x. Instead of writing the cos function, you can write this as, so this is actually immaterial whether you write this as a cos or a sine function. So, this is, you write this as alpha small x. Now, this equation that I have given you, that we have formulated, this is a linear system, there is no non-linear term. So, neither you are producing a square term or a cubic term out here. So, this is a linear system. So, this you write this as a linear system. Now, this linear system is giving output as capital X t. Now, here you write capital X with a cap, and again since sine is out here, so the response also will be in a sine function. So, this is 2 pi f t, f is your frequency, plus now there will be change in the phase angle. So, you write capital X. Now, you do not, same thing, x small x, you do not put it out here. So, you write this capital X t. So, we are seeing what is happening. So, A and B are the constant which are remaining the same, but x t, you see that this x cap is your amplitude. So, x t is this, so which I have already written. So, this is f t plus alpha x. So, there is only difference in amplitude and phase. So, differs from, so differs from small x t. Now, small x t, you have written this as small x with a cap multiplied by, you are doing it for the same frequency, that is 2 pi f t plus alpha x, small x. So, you write this differs in amplitude and phase only. Now, this is very important. So, differs in amplitude and phase only. Now, this is to be noted. So, this is given by this x cap, capital X cap and small x cap, and here also that is this amplitude difference, phase difference is there. Now, you write your amplitude response function. So, this actually in naval architecture we call this as response amplitude operator. So, here this is written as R cap F. So, this is your capital X with a cap. F denotes that this is a, these expressions are dependent on frequency, small x you write. So, this is just the ratio of the amplitudes of the response to the excitation. So, this is called a amplitude response function. This is a amplitude response function. Now, this is where we are interested, because we are more interested in getting this value of x from your wave. Now, the wave amplitude you know, that is your coming wave amplitude you will get from the wave spectra, right. Now, these how to get capital X F, this is where your heave response or pitch response will be this XF. So, you get this in naval architecture we call this as RAW. You will find this very common. So, your naval architecture book you RAW, you will find RAW, you have to calculate this RAW for heave, pitch and roll. Now, this is not easy to calculate. Now, you have to find this from sea keeping experiments. Now, sea keeping experiments you cannot do that in a towing tank. Now, what we have got is a towing tank. So, this is done in a sea keeping basin or in a sea keeping tank. Now, this Madras IIT has got, which we do not have. Now, the speciality of this sea keeping basin is that you have to produce a random sea, or you have to produce the sea surface elevation. So, that is called a Gaussian surface. A random Gaussian surface wave has to be generated for your sea keeping experiment. Now, only after you do this sea keeping experiment, you can calculate this RAW for heave, pitch and roll. So, this is where we are more interested, but unfortunately experiments you cannot conduct in our wave tank. So, anyway, so this is called your amplitude response function or amplitude response vector. Now, so this is just the ratio of the amplitude of the response to the excitation, but what about the phase angle? Now, the phase angle you will find this is given as this alpha, and that we do not write this as the ratio of two phase angles, but rather we take the difference. So, this is actually the difference of the two alphas. This capital X is your response and the other one is your excitation. So, this is your phase, or rather this is called a phase response function. Now, phase response function, you simply remember that this is the difference between the two phases. You do not take the ratios of the two phases as you have done for the amplitude. Now, from these two, how you get the response spectra? Actually, in your measurements from your sea keeping tank, you do not measure directly these two ratios of the displacements, because that will cause error. But rather you have to take the energy spectra. So, how do you get this EXF? This is called the response spectrum. Now, your response spectra, that is the spectra is always that we have analyzed from our previous class, that it is always the square of the amplitude. So, that means you square this RF. So, this thing that you have found out, this has to be squared, because we are dealing with the amplitude. Now, this square you multiply by the wave spectra. So, this is small x. So, this is capital X. Now, capital X stands for your response and small x stands for the wave. So, this is how you will obtain the response spectra from what? From wave spectrum. So, ocean engineers, they are more interested in this wave spectrum and your response spectrum. So, this is what we will obtain. Now, this is actually not having any direction. So, this is not having any direction. Now, if you introduce direction into this, then this RF theta, you just introduce another dimension, that is all. R, the frequency, and the direction of propagation of the wave, that is denoted by this theta. So, here of course, if you make this, then this will be capital X, this will be f theta, and this will be small x. This is the only change that you will be required. So, introduce another parameter, that is theta, that is all. So, EXF will be how much? So, if you get RF theta, so obviously your response spectra will be, so this you write in bigger terms. So, this is f theta, you just square this one. So, this will be R f theta square, you square it and replace x. So, Ex will be your wave, but then you have to do the f theta for your, you introduce the direction spectra from the wave. So, this is your response. This is wave direction spectra. Now, in ocean engineering calculations, this is either you get this if there is a direction spectra, or you get this EXF. Followed. Now, here there instead of directly calculating this RF theta, you calculate this RF square, and you know your this EXF. This is what? This is your wave spectra. So, wave spectra you can either obtain from John-Swap, Pearson-Moskowitz. If you get, you multiply by this RF square, you get this. Now, what they do is, normally if you want to find this RF square, you take measurements in your sea-keeping tank or a sea-keeping basin. Okay. You have, there are two things which you will have: the ship. You can generate this in your sea-keeping tank. So, you measure the response of the ship, you make a model. Okay. Say this is your wave, you put a, say, accelerogram or a motion measuring that LVDT. Okay. You can now measure heave by an instrument called LVDT mounted on the ship. You can measure that. So, this you can measure, that is, say, example is the heave response, and you have a wave buoy or a wave probe. Say this is your LVDT, and this what you require is a wave probe. Now, wave probe will give you the wave elevations or wave displacement, wave amplitudes. Now, from these two things you can measure this thing EXF. You can plot your, this is actually giving your excitation, isn't it? From the ship you are getting the excitation, and from the wave probe you are getting the ship is giving the response. So, here you are getting the response from this LVDT, and this is giving you the excitation. Forward. So, this you can get the displacement from these two instruments you get. Now, what you do is you get this value. Now, actually you have to find out this motion rouse. So, this square is what? So, this you can get it from the sea-keeping tank. Sea-keeping basin, normally you measure the ship response and the wave probe will give you. So, these two spectra you can obtain. You divide this, you get the square of the rho. Now, from this rho you can get a square root of this. So, that is how you can obtain the response. So, this brings us to the end of the discussion on the spectra. Now, next class we will give you some description of these offshore structure before we go into the structural mechanics.